Fabulous. All right, we are, see, last week we just had the one assignment, just the 3.03 theorems of algebra, which we had a video lesson for since we didn't meet last week, Monday through Wednesday. So this week we've got two lessons, and we're getting into some pretty deep stuff. So you will need to go through and read the lesson in Buzz, in addition to the examples I'm going to give you. I'm going to try to make it a little easier to understand. But we're looking at the rational root theorem and Descartes' rule of signs. Both very, very useful, very useful information, but pretty detailed. You have to pay attention. You got to pay attention to what you're doing. So I'm going to put up on my screen here my pencil and paper, and we're going to talk about what these assignments tell us. So, okay, so we learned the fundamental theorem of algebra. It talked about the different roots, and we've learned about long division and synthetic division, which is very useful in all this. So let's say we have this equation here, f of x equal, and let's see, it's x to the fifth plus 2x to the fourth minus 4. Oops, my pencil broke. Get too excited here. All right, that'll work. All right, 4x to the third minus 4x squared minus 5x minus 6. Okay. And what if I said we need to find all the zeros or all the solutions or all the x's that would be the solutions for this equation? And we're like, oh my goodness. Well, we learned from the fundamental theorem of algebra that this has 5 roots. It has 5 zeros. It has 5 solutions because the largest exponent is a 5. So there are 5 solutions to this. So I said, okay, so what are they? And like, oh my goodness. Well, we learned using division, synthetic division, that if we just divide a number into it, and the remainder is 0, then that is one of the solutions. It's like, well, will I just start at 0? Do I start at 1 and just keep dividing numbers in there? Do I do the -1? We could spend a long time trying to figure out what are the possible solutions to this. Well, there's something called the rational root theorem. Let's look at the rational root theorem. This will tell us how many rational roots, because there's rational roots, there's irrational roots, and there's imaginary roots. There's 3 different kinds of roots that it could have. But this will help us figure out what are the possible rational roots. So what you have to do is you have to look at the coefficient of the first term, which is just a 1, right? There's no number there, so it's a 1. And you got to look at the last term. And we got to figure out what are the factors. Well, the factors of 1 are pretty simple. We'll just guess to keep focusing and refocusing. Factors of 1 are either 1 or -1. So we can say plus or minus 1. That's the only possible factors of 1. You can either multiply -1 times -1 and you get 1, or +1 times +1. So for 6, you can take plus or minus 1 times plus or minus 6. I'll put the plus or minus 6 down here at the end. And plus or minus 2 times plus or minus 3. That's the only numbers you can multiply together to get 6. Right? So the rational root theorem talks about putting P over Q, and it calls the P is this right here, the last constant, and the Q is it's P and the Q. So if we take the P, 1, and put it over 1, that's just 1. So these are all over 1. So since they're all over 1, the factors are, let's move that over a little bit. Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. So that's the only possible rational roots there can be for this. So that narrows it down. There's only 8 numbers that could be a rational root. That doesn't tell us how many irrational or imaginary roots there are. It just tells us that. But now we know we can start with this. So if we use synthetic division, we'll start with 1. Let's see if 1.
Wait, Mr. Brock, can you go back? Can you go back to where you're explaining like the Q over P thing?
Okay. Let me give you a different example to explain this P over Q a little better. What if this was 2x to the third minus 4x squared plus 3x plus, and we'll make this a 5.
Okay.
Okay, in that case, the P is the 5.
Okay.
The Q is the 2. It's always the largest exponent.
Okay.
The coefficient of the largest exponent. So what are all the factors of 2? It could be 1 and 2 plus or minus. All right, that's how many different ways we can multiply and get 2.
Yeah, twice.
Right, and 1 and 5 plus or minus is the only way we can get 5. So that tells us the factors, the rational factors of this would be P over Q. It'd be 1 over 1, which is just 1. It'd be 1 over 2, which means it could be 1/2 plus or minus. 5 over 1, so it could be 5, or it could be 5/2. Because we just take whatever, all the possibilities of P and put them over all the possibilities of Q.
Okay.
1 over 1, 1 over 2, 5 over 1, and 5 over 2.
Okay.
Which simplified to just 1 and 5, and 1/2 and 5/2.
Okay.
Now up here, since all of the Q's are 1, we just use all the P's because putting this over 1 just equals the same number.
Oh, okay. That's why I didn't. Okay. I get it now.
Yeah. Well, P over Q just equals all the Q's because everything's over 1 for this one. So yeah, it helps to look at one that's not 1 to understand what's going on there. Okay, that was a great question. All right, so let's look at our coefficients. 1, 2, -4, -4, -5, -6. So if we want to know if 1 is one of our solutions, this just comes straight down 1. 1 times 1 is 1. We add those together. 1 times 3 is 3. We add those together. -1, we add those together. -5, add those together. -10. Okay, so this has -16 as a remainder. So +1 is not a solution. It's not one of the factors. Let's look at 2. We're probably not going to do all 8 of them, but we'll at least do some here. So 1, 2, -4, -4, -5, -6. So if we bring the 1 down, 2 times 1, love synthetic division. This is so much easier than setting it up as long division. 2 times 1 is 2, add those together. 2 times 4 is 8, add those together is 4. 2 times 4 is 8, add those together is 4 again. This is 8, add those together is 3. 2 times 3 is 6. Oh, 0 remainder. So 2 is one of our roots. +2. That is one of the 5 solutions on there. And we could continue to keep going through all of these. We can do 3, we can do 6, then we can turn around and do the negative ones. But before we get too far in this, I want to talk about one of the other things that is in this lesson, and it's Descartes' rule of signs. I'll put this on a different page here. Descartes, he was a Frenchman, 1700s, and he discovered this for us, Descartes' rule of signs. And Descartes' rule of signs say, okay, if we have this long equation here, we have this very long equation, all we need to look at on it is how many times did the sign change. So it starts with a positive x to the fifth, and it has a positive x to the fourth, and this is a negative x to the third, and a negative, and a negative, and a negative. Right? That's just taking the signs. This is a positive, a positive, a negative, a negative, a negative, and a negative. Descartes says, how many times did this change? Started as a positive. Oh, there's a change. Changed once. Changed from a positive to a negative. But it never changed again. So according to Descartes' rule of signs, there is only one positive root. One positive root. So there was no need to check the 3 and the 6 because they're not going to be roots because we already found a positive root. There can only be one positive real zero. Now, this doesn't tell us about an imaginary zero. There could be an imaginary zero. But this is saying as far as a real positive root, there's only one. Now, it can also tell us, because there's still possibility of 4 negative roots, right? We have 5 roots. Maybe one of them is positive and 4 negative, and there's no imaginary. We don't know yet. Descartes can also tell us how many negative roots there are. And this is how. We go into the original equation and we change the x's to negatives. Negative x to the fifth plus 2 negative x to the fourth minus 4 times negative x to the third. And everywhere there's an x, we replace it with a negative x. We just go in and we substitute. Minus 5 times negative x minus 6. So we take the original equation, and everywhere there was an x, we replace it with a negative x. And then we simplify it. So negative x to the fifth, right? Negative x to the fifth is negative x times negative x times negative x times negative x times negative x. Right? It's multiplying negative x times each other 5 times. So when you multiply 2 negatives, this is x squared. And then we multiply it by the next negative x. Now it's a negative x to the third. All right, we're going to take that one. Now we multiply it by this negative x. We multiply those together, we get a positive again, x to the fourth. And then multiply it by another negative x to the fifth. Positive, negative, positive, negative. It ends up negative x to the fifth when we simplify it. Negative x 4 times. Negative x times negative x is a positive x squared times another one's a negative x to the third times there's a positive x to the fourth. So this remains a positive. So this whole thing, positive 2 times positive x to the fourth, stays a positive. Okay, negative x to the third. Negative x times negative x is positive x times the negative x is negative x to the third. So this becomes negative 4 times negative x to the third. Well, a negative times a negative makes it a positive 4x to the third. All right. All right. Let me make sure, keep it up with our lesson has. Negative x times negative x is a positive. So this becomes negative 4x squared because a negative 4 times a positive x squared, negative 4x. Negative 5 times negative x. Well, that's a negative times a negative. So that's positive 5x minus 6. Okay, this is what our equation becomes when we substitute negative x into it. So again, we just need to take the signs. Negative, positive, positive, negative, positive, negative. Negative, positive, positive, negative, positive, negative. This changes, stays the same. Oh, changes back to a negative, changes back to a positive, changes back to a negative. So there is possibly 4 negative roots. Now, here's the thing about Descartes' rules. If it says 1, then there's definitely 1 positive. But it could be that some of these negative roots may be imaginary. And if there's anything we remember about imaginary roots, is if, let's say, for example, we had -2 plus I. If that's an imaginary root for an equation we have, that guarantees that -2 minus I is also a root, because imaginary roots come in pairs. Whatever the plus is, there's also a minus. If the root was 3 minus 5I, that means 3 plus 5I is also a root. They always come in pairs. So if it turns out that some of these are imaginary, maybe there's only 2 negative roots and 2 imaginary. It's possible, because we don't know how many of these are imaginary, how many are real. Since there's still a 2, there could be 0 negative real roots, and there could be 4 imaginary. There could be 2 pairs. There could be 2 pairs. All we know is they come in pairs. But since this says 1, we know there's no way the 1 is imaginary, because there has to be pairs of them. So anytime you have a number that's 2 or larger, you have to remember, could be that a pair of them are imaginary. Anytime that you have 2 or larger. So now we know for this original equation that there's going to be 1 positive, and there's either going to be 4, 2, or 0 negative real roots, and there will be 0 imaginary, or 2 or 4. But there will be 5 roots, because we know that from the fundamental theorem of algebra. We just don't know for sure how many are negative and how many are imaginary. We do know one of them is positive, because if this comes up where there's 3, let's say there was 3 positive. If there says 3 positive, and that's a terrible, wrote that terribly. That means there could be 3 positive real roots, or there could be 1 positive and 2 imaginary. Right? Because if any of those are imaginary, there's going to be a pair. But we know there's definitely at least 1, because we can't go to -1 positive roots. So again, there are videos in this lesson that help you go through that. There's examples in this lesson to help you go through that. And it's important to try to work the examples they give you so that you can see if you are correct, because it has on there where you check your answer. Okay, let's see. It's got...
How do you know when a root is imaginary or negative?
Okay, here's a... I got this other example here. We have one. If I can find it real quick. I have an example of one that's turns out to be, we can check it. Yep. If it asks you, if it's just asking you how many possible roots there are, the answer, if you don't have to actually find the roots, is usually given as like a table. Roots. Positive, negative, imaginary. Like for this one that we just did, we know that there's 1 positive, okay, regardless of how many negative and imaginary are. We know there's 1 positive because that was the only number, 1. So there can't be a pair of imaginary. So there could be 4 negative roots and no imaginaries, or it could be that there's 1 positive, 2 and 2, or it could be that there is 1, 4, and 0. Unless that we're asked to find what the roots are, this is our answer on how many roots there are. It's either this, or it's this, or it's this. And without further solutions, this is all we know. And they all total up to 5, right? There's 5. We know there's 5. So it should total up to 5. We just don't completely know the breakdown unless we have to take that next step and actually solve to tell what they are. Let's see if we got a good example. We can use.
And to solve, you have to do the division, right?
The synthetic division is how you would start finding real roots. Now, rational roots. Now, the problem is you could also have irrational roots.
Oh my gosh. Okay.
Which with irrational roots, then you got to go to the quadratic formula, which means you got to get it down to an x squared, which means if you find 2 as a root, divide that 2 out of there and get it down to x to the 4th, and then find another root and get it down to x to the 3rd. You can't use the quadratic formula until you get it down to x squared, because that's the only time that works.
Yeah.
Okay, let's see here. So our assignment, I'm going to look at our assignment real quick. Put it up on our screen. See what kind of questions it's asking you. Like the first question is, what are the possible rational zeros? Well, that's where you do the P over Q. Yeah, Q is the coefficient of x squared, which is just 1. P is 14. So you take all the possible roots of 14 and put them over 1. You list those there. What are the possible rational zeros? See, that's the same thing. Possible rational zero. Same thing here, except now you have 2 as a coefficient and you have 22 as your constant. Here's one of those where it says, what are the possible numbers of real, positive real, negative real, and complex? This is where, again, there could be 2 or 0 or 2 or 0 of negative or complex.
Complex is just imaginary,
yes,
right?
Yes,
okay.
Absolutely. That's another word for imaginary. Complex zeros, because they have a real portion and an imaginary portion, so they're a complex number. So
okay.
So that's what these are asking for. It's not asking us to find those to figure out exactly. This is just talking about figure out what possibilities there are. You know, is it possibly 2 real and 2 complex, or is it 2 negative and 2 complex, or is it 2 positive and 2 negative? You know, so there's 2 of those, and then the last one. This is good. Well, I want to look at graphing. I want to look at graphing. So let me move this back out of the way. So when we talk about graphing, when we know the roots, when we find the roots of an equation. And let me see if it gives me a good example in our problem, so I can use an actual. Okay, so if we, and this would be a lot of work, so I'm just gonna cut some of the work for time's purposes here. If we had f of x equals x to the 3rd plus 2x squared minus 11x minus 12. Okay, we could use our rational root theorem and take the factors of 12 and the factors of 1, and that would tell us that all the possible ones would be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. right? 1 times 12, 2 times 6, 3 times 4, positive or minus in any combination would give us 12 over 1. Right? So there are a dozen possible numbers that we might have to use synthetic division to figure out which of those 12. By using Descartes shows us that the sign changes positive, positive, negative. Sign only changes once. There's only one of those positive roots. And we could substitute in a negative number and find out there could be 2 negative or 2 complex. We know there's only 3 total because it's the x to the third. So doing that would rule it down to where once we figure out the positive one, we can stop checking the rest of them. Once we find 2 negative ones, we can stop checking it. And if we did that, here's what it would show. It would show -4, -1, and 3. That is actually the 3 zeros that work when we do synthetic division. That's the ones that will give us that. Now the question is, could we graph this? Can we graph this? Actually, we can. If we have the zeros, well, zeros actually mean that on a graph, that's where the function equals 0. So at -4, we know that that is a point on the graph at 0. When x is -1, that is a point on the graph. And when x is 3, the function also equals 0. So that's a point on the graph. The other thing we know is the y-intercept. That's when x equals 0. If these are all 0, 0, 0, -12 is the y-intercept, which on our graph would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Be way down here. Okay, so it's almost off our graph. So knowing that this is an x to the third, an odd numbered function does that, right? An odd numbered function looks like this or looks like this, one way or the other. But one end goes up, one end goes down if it's odd. That's always true if it's odd. So with this, we know that since the y-intercept's down here in between these 2 points, this must go down and then come back up. And so this must go up here somewhere. We don't know exactly where. But that is just a rough sketch. It's not exact. There's no way exact. This point is probably wrong. This point is wrong. Several of these points are wrong. But we know the behavior of what the graph will do. This graph, x to the third plus 2x squared minus 11x minus 12, will look something like this. But we've got the important parts. We've got the zeros and the y-intercept accurate. So let's put that on Desmos just to see what it really, the actual graph of it looks like. We're going to put it up here on the screen. Desmos calculator. We'll put y equals x to the third plus 2x x squared minus 11x minus 12. Well, that's about what we did. Now, see, it crossed here at 12, but it actually went down much farther. We didn't draw it down a whole lot farther. And it actually goes up above over 12. You know, so we didn't draw it as extreme. It should have went up a lot higher, and it should have went down farther down below the page here. But that's roughly the same graph. You know, that is roughly, we still got the same end behaviors. We have the same y-intercept. So as long as we have the x-intercepts, 3 x-intercepts, -4, -1, and 3, -12. If it just says to sketch it and all you have is those points, this is fine. This is accurate. It gives us some idea what the graph would look like. So if it gives us some graphs, we should be able to tell which one is the right graph for the equation. If we have the equation and the zeros, we can look at graphs and say which one has these zeros, which one has this y-intercept. That would be the graph that matches this equation. So it gives us a lot of tools that we didn't really necessarily think we had to start with. That is the primary section of lesson. Let me see. I think the summary is down here. Yeah, lesson summary. For lesson 4, lesson summary is the rational root theorem, where you take the P over Q and figure out what are the possible factors. This only has 11 in 1 and 3 in 1. So it's either 1 plus or minus 1 plus or minus 11 plus or minus 1/3 or plus or minus 11/3. And yes, a lot of times you'll end up with fractions like that. Then Descartes' rule, which, by the way, they have a nice little flow chart you can use to find out how many times it changes. Reading from left to right, count the number of times it changes. Negative, negative, positive, positive, negative, positive. So it changed once, it changed twice, it changed 3 times. That changed 3 times. So there's possibly 3 positive real zeros. But we can also subtract 2 from that. So there might just be 1 positive real zero. All right. And then when you see number sign changes, could be 3 or could be 1. For negative real zeros, you have to substitute. There's that 3 or 1 talks about right there. You got to substitute negative x into your equation and simplify it. So they do that right there. That changes to plus, minus, minus, plus, plus, plus. So it only changes twice. It changes once to a negative and then changes back to a positive, and that's it. So that means there could be 2 or there could be 0 negative. All right. And so once you start figuring out, but here's all the possibilities. We know there's 5 total. So there's either 3, 2, and 0, 1, 2, and 2, 3, 0, 2, 1, 0, 4. One or the other. One of those 4. And then graphing that. So the next lesson, looking at lesson 5, 3.05, it's just about solving polynomial equations. So that's taking all this stuff that we've used and actually solving equations with it. So it gives you reviews of all of these: the fundamental theorem of algebra, the rational root theorem, Descartes' rule of signs, the remainder theorem, and the factor theorem from last lesson. And it's got summaries of all those. And it has you walk through the steps on how you would solve an equation. X to the third plus 3x squared minus 22x minus 24. So use the rational root theorem, tells you how. Descartes' rule of signs tells you how. Fundamental theorem of algebra. And all of that is helping you narrow down the answers, where you don't have to test all these wild numbers. Test the factors. So they narrowed it down to 4 numbers. They narrowed this down to just 4 numbers to test. And then writing the depressed equations, where you go ahead, once you find one that has a factor of 0, okay, now this takes it from x to the third down to an x squared. They're calling that the depressed equation, right? Because we're factoring one of the factors out already, and that's what's left. It tells you more about depressed equations. Find the zeros. And now that you've got it down to a quadratic, you can use the quadratic formula and the discriminant. So this walks you through that. Look at the graph. Here's the graphs. Confirm the zeros by substituting. Those are all in there. Several steps. So you need to go through these steps. You need to understand the steps to do that. Here's another video on using the rational root theorem. This video is 8 minutes. It goes through a lot of detail to show you how to determine the zeros of this equation, and then sketching the graph of it. Here's another one. What is the p-value of the function? This is where you can test. It gives you this function right up here. What is the p-value for that function? So you submit that, see if you're right. It's got 5 different things that ask you about. After you get done with those, go to step 2. How many times does the sign change? This is using Descartes' rule. Can you go through that and accurately tell how many times it changes? Submit that answer. Step 3, determine the zeros now. After going through those steps, that gets you a lot closer to determine those zeros. So, and remember, the conjugate of a binomial is another binomial whose terms are identical. Like conjugate 3 negative square root of 5, 3 plus square root of 5. If it's imaginary, 7 plus 10i, 7 minus 10i. It talks more about solving polynomial equations here. So solving equations is what it all really is about. We just have all these other theorems that help us make that a shorter process. Otherwise, we could spend an hour solving one polynomial equation. If I gave you an x to the 5th equation, you could spend an hour doing that. But these theorems will help you narrow that down to where you're using your time smarter and not having to spend all that time checking every possible number it could be. There's another video that will walk you through that. This one is 2 minutes. Another example down here. There's lots and lots of examples built into here. And here's the lesson summary. This lesson is only 3 pages. Lesson summary right here on how to solve equations using the different theorems that we've just learned. Okay. Now, why is there more pages? Well, because now it gives you examples for you to practice. Practice. You try. Determine the zeros of each function and then drop it. Which one of these functions is x equal to a rational zero for? Drop it in there. And it'll have several of them. As you drop it, it'll give you another one. Then you figure that one. But which one does that go in? Drop it. Drop it. Then there's moral practice over here. Write the polynomial function with the given roots. Oh, this is a good one for do. We haven't done one of these on paper. Let's do this. All right, we're going to do this one together. Write a polynomial function. What if we already have the function? I mean, we have the roots, but we don't have what the function is. This says 4 of multiplicity 2 and -1. Okay, what's that telling us? That's telling us that the roots are 4 of multiplicity 2, means there's 2 4s, and -1. That's all we have are the roots. But we don't know what the equation is, and it's asking us, what is the equation? If we have the roots, we can make the equation. If the root is 4, then that would be x minus 4. Excuse me, as the binomial for that equation. Because 4 is where it equals 0. So 4 minus 4 would equal 0. We have another 4, which means there's another x minus 4. And then we have a -1. So x minus -1 means it's x plus 1. So if these are the number roots, these are the binomial roots. You change the sign and put it after an x. And now to write the equation, these are all multiplied together. X minus 4 times x minus 4. Let's do that one first. X times x is x squared. X times -4 is -4x. Okay, that's just taking the x and multiplying it by both terms. Now we have to take the -4 and multiply it by both terms. -4 times x. -4 times -4 plus 16. Still, we have to do the x plus 1. Let's simplify this first. X squared minus 4x minus 4x. Well, that's minus 8x plus 16. And then we still need to multiply it by the x plus 1. Okay? So I'm going to go ahead and I'm going to move this in front of it just to make it easier to distribute. You can do it either way. But the first thing I need to do is I need to take this x and I need to multiply the x times the first term, x times the second term, and x times the third term. All right? So x times x squared is x to the third. X times -8x is -8x squared. And x times 16 is 16x. Now, I need to take the second term, the -1, and multiply it times the first term and the second term and the third term, right? We have to distribute into the parentheses. -1 times x squared is -x squared. -1 times -8x is a positive 8x. -1 times a positive 16 is a -16. Now it's just simplifying. There's only one x third. -8x minus another 8x squared minus another x squared. So that gives us -9x squareds. And we got 16x and another 8x. So that's 24x. And then we got a minus 16. So this is the polynomial that has these roots. So if it wants us to write the polynomial and it just gives us the roots, we just multiply them back together. Now let's prove that to ourselves that we're correct. Let's see, do I still have the Desmos window? I do still have the Desmos windows. All right, so let's change this to x to the third minus 9x squared plus 24x minus 16. That's what we said it was. Now, if we look at the graph, we see it at 4, it bounces. It does not cross the graph. That's true when you have two roots of the same. And we have two roots of 4, so it bounces. And this is 1. Now, we messed something up there because our root was -1. So somewhere we've got an incorrect sign. Did I type it incorrectly? I did. Oh, I see what I did wrong. Look here, when I moved this over here, I wrote it down. This is x plus 1. I made it a minus. I changed the sign. So I need to do a positive. So this is a positive x squared, a negative 8x, and a positive 16. So now let me redo this. X to the third, there's only one of those. X to the squared, so this is only -7. See, I changed the sign right there. I switched it. So -8x squared and positive x squared. Positive 16 and -8. So that's just a positive 8. And then this is a positive 16. So let's update our equation in Desmos. So this is -7. This is a positive 8. And this is a positive 16. There we go. Now the roots are -1. And there's the double root at 4. Anytime there's a double root, it will bounce off of the x-axis instead of crossing it. If it's a single root, it will cross it. But now we have the correct roots. All right, got to be careful. See, even the teacher makes mistakes. Don't change the equation when you move it. I changed it and made that a mistake right there. All right, so that's how you take roots and you make an equation out of it. If the root is 4, then it's x minus 4. Because if x minus 4 equals 0, that means plus 4. That means the x equals 4, which was what we had there. So the equation is x minus 4. Okay. Oh, that's not what I want there. Just back over here. So this has that 4 multiplicity of the 2. Then they have another one. Oh, that was okay. That was there. And the other practice problems it has is over here on page 5. Determine the zeros of this. After you figure out what the zeros are, there's where it has you check it. All right, there are either 2 or 0. 8 steps. There's the next step. Next step. So it's all there where you can check your work all the way to the end. And say, solving some of these big polynomials are x to the 4th and x to the 5th, a lot more time involved. What does that mean if there's a lot more time involved? That means if you're not practicing these, you won't be able to do these. This is where you really have to go through and you have to do the practice problems. You got to get some pencil and paper. You got to work through these things. If you don't practice it, and I put a test in front of you, I guarantee you can't do it. You just can't do it if you don't practice it. That's how a lot of math is. The more you do it, the easier it is. You look at it, it's like, oh man, I could never do that. Yes, you can. You just have to do the practice. And it's best to get in the lesson and do those practice problems first because it lets you check your answer. If you just jump straight to the assignment, Okay, well, maybe that's right. I don't really know. Yeah, you don't. But if you do it in the lesson first, you have that opportunity to double check your work and go, okay, I knew what I was doing. My answer matched their answer. That's great. Or I was off. What happened? Oh, there it is. I missed that negative, because it'll show you all the steps to get there. So, that was almost an hour's worth of stuff. I know this is a long time for a virtual class, but this is pretty deep stuff. And I want you to understand how important it is that you need to go through these 2 lessons and you need to do those practice problems. So be sure and do it with pencil and paper in front of you, so you have that opportunity to do the practice on there. So, all right. If you have any questions, hang around. Otherwise, that's all I'm going to keep you today. I will not be here on Wednesday. So you have to email me. I'll be out Wednesday and Thursday this week, but I'll be here Monday, Tuesday, and Friday.